Okay, good afternoon, everyone. So this week's tutorial is based on chapter 11, that is multi-rate signal processing, right? So there's four questions that we need to discuss, right? Those are 11.5, 11.9, 11.12, and 11.13, right? So let's start with question number one. So question number one says, in this problem, we illustrate the concepts of sampling and decimation for discrete time signals. To this end, consider a signal x of n with a Fourier transform x omega as in, right? This is the signal that is given over here that we'll have to consider for the following parts, right? That follows. So part A is sampling x of n with a sampling period d is equal to 2 results in the following signal, right? So this is a signal that we result into. So basically we have a value x of n for the sampled signal x of n when n is equal to even, and otherwise it is 0, right? So yeah. So it says compute and sketch the signal xs of n and its Fourier transform xs of omega, right? Can we reconstruct x omega from xs of n, and how? So the first thing that we need to do is to first try to find the Fourier transform of this particular signal that is given over here, right? So if we try to do perform a Fourier transform of this particular signal, right? So you can see that what we can do is, if we write this using the Fourier definition, we'll get x s of n e to the power of minus j omega n summation of that, right? Okay, that is also equivalent to summation of x of 2m e to the power of minus j omega 2m. So in this particular case, 2m is also identical for a even signal, right? Or dm. That this is decimate. Usually we can write it as dm, right? So d is our decimation values, that is 2, right? So so we can write this signal as this, right? However, in order to derive the Fourier transform of x s of omega in terms of the original frequency response, right? That is x omega, right? In terms of this particular graph, in order to derive the sample frequency omega in terms of this particular graph over here, what we need to do is to rewrite this x s of n, right? So based on, let's say, well, based on your textbook, if you go to page number 756, actually. So it tells you about the downsampler, right? How a decimation works, right? A decimation is basically downsampling or reducing the size of the samples that you have, right? So there's a whole notes on this. So I hope you guys have covered it. But so so what you can do is, let's say we have a signal that is v of n, right? We have a signal v of n that goes just before passing on to we have a signal v of n just before it passes down to a downsampler, right? And we get a downsample signal. We have a signal v of n, right? So what happens if we go over here? If we see this particular graph, you can see we have a signal v of n, and then it goes through a multiplication, and then downsampling happens, and then you have this particular signal over here. Just before downsampling it, right? What happens is you can represent all the missing points over here that has been downsampled, right? In between, like this signal has been downsampled, isn't it? So all this missing point could be represented with zeros in between, right? So that we get a signal v of n, which is equal to v of np times n, right? So if we go back over here, right? In this particular case, we can see based on the question that we have over here, right? You can see this particular sample signal x of n is true. I mean, you have a sample signal that has a value when n is equal to an even value, right? And when n is equal to an odd value, right, it is basically 0. So you can basically link it to this particular signal over here, right? It is basically the same thing, right? In our case, our n is 2. I mean, our d is 2. So that is why 0 plus minus 2, comma plus minus 4, so forth is written in our case, right? So you can see this over here. it is corresponding, right? Isn't it? So in order to obtain this particular sample signal, right? So let's just forget about whatever I just said, just about the downsample. Let's just focus on this main signal that we have v of n. V of n is basically equivalent to our x of n based on our question, right? And this v bar of n is basically our sample signal vn, right? So in order to obtain this signal, what we can do is we can multiply v of n by a periodic train of pulses, right? That is represented by p of n, right? So if you multiply v of n with p of n, right? P of n is basically given by this, right? And d is basically our decimation value, right? Our downsampling value that we can use, right? So basically our sample signal can be represented by this, right? So now if we do that, right, in our case, our sample frequency is basically, I mean, the Fourier transform of our sampled signal is basically equal to xs of n multiplied by e to the power of minus j omega n that we have over here, right? In our solution as well, we have that, right? Now, how do we go from here till here? This is equal to this, but how do we go from here to here? Now, that is by using the pulse train that I have shown over here, this particular function and this particular term. In our case, the question is in terms of xs of n, right? V bar is basically represented by xs, right? While v of n is basically represented by x, right? X of n. So it is the same thing, just multiplying. Now what we are doing is just multiplying by a pulse train, right? Isn't it? In order to get our sample signal. So same thing, if we do that, right, we can replace this sample signal with x of n multiplied by p of n, right? And where our p of n is basically equal to 1 upon d, summation of e to the power j 2 pi k n upon d, right? From k is equal to 0 till d minus 1, right? Now, what we can do in place of p of n, we can replace this particular term over here, right? That we have. We have said that p of n is our basically a periodic pulse train. Right? So we can take that and we can replace it, right? Replace p of n, and in place of k, we can use q, right? So that our solution matches to this particular k, right? I have just done it like that. You can use k no matter what it is, right? We'll be getting the same answer at the end of the day. Now, now we have written this into this particular form. We have expanded this, right? Now what we can do is we can reorder this, right? We can sum this term, or we can find the Fourier transform and then find the summation, right? We can take this particular term, this summation part, right? So we can basically reorder it. So we reorder this sequence, we get this particular term, right? In this particular sequence, right? I've removed this t minus 1 over here, so just avoiding the t minus 1 over here in this particular case. So the summation is in terms of k, right? And over here, the summation is in terms of n, right? The summation is in terms of n. The summation is in terms of q. So I guess everyone will understand, right? So we can reorder these terms, right? So that we get this particular term over here. Now, based on these, you can see that based on the original term, it is this summation was in terms of n in order to find our Fourier transform, right? Now, if we take the Fourier transform first, right? We take the Fourier transform of this whole equation. This x of n multiplied by e to the power of minus j omega n is basically the Fourier transform, right? That is x omega. Now, e to the power, multiplying these particular terms with e to the power of j 2 pi n q holding upon d is basically using the frequency shift property, right, of a Fourier transform. We can basically see this is a shift in frequency domain, isn't it? So basically, we can write x omega. We can reduce this whole term, right, as x of omega minus 2 pi q whole thing upon d, right? That is summed in terms of q multiplied by 1 upon d, right? Now we know our d value, isn't it? Our d is 2. So if we replace d with 2, we get 1 upon 2 summation in terms of q of x of omega minus pi upon q, because d is 2. So this d will cancel out with this 2, isn't it? So we are left with omega minus pi q, right? We can also remove this q part because I haven't done it, but we can remove it because our d value is 2. So our value becomes, oh no, we cannot directly remove it, right? But however, we can expand it. But if d is equal to 2, so our summation will go from 0 till 1, right? However, we have the solution over here. So this is basically in terms of our original x omega. So based on x omega, we can see, right? We can translate this. Our x omega signal is given over here. We can see the amplitude is reduced by half, right? And it is now, what happens to the period? Periodic in terms of half, I mean, in terms of pi, isn't it? So if we draw this signal in terms, if we draw the sample signals frequency response in terms of this signal over here, we get something like this, right? Okay, so this becomes our sample signals frequency response. Now, can we recover the sample, the original signal x of n from the sample frequency? Yes, we can, right? What do? We interpolate or we upscale, right? We interpolate or we get the missing points, right? We increase it by 2, and then we pass it through a impulse response, right? Low pass impulse filter, right? To get our x of n back, right? So that's how you get it back, right? So if I go back to these particular block diagrams, the order with which we can perform this is can I find the diagram? I'm not sure. Okay. Unfortunately, I missed out on that, right? So what has happened over here is basically that in order to decimate this, right? In order to decimate this particular sequence, we pass it through a low pass filter, and then we obtain a then we downsample it, right? In the inverse process, the inverse of decimation is interpolation, right? Everyone understands what interpolation is, I guess, right? That is basically plotting the missing points, right? Isn't it? While the opposite of that is decimation. You remove the points, right? You decrease the size of the sample, right? So opposite of this, we have first pass this signal through a low pass filter and then through a decimation signal, right? So now opposite of that will be, let me just quickly draw it. Okay, I can draw it. I forgot about that, right? So we have a low pass filter, and then this goes through a downsampler in order to get our output. So this is my filter, let's say H, L, and this is my downsampler, right? By 2 units. And then this is my X of N, and this is my sample signal S of N, let's say, right? Now, if we need to obtain our original signal, what do? We go back, isn't it? So what happens? The first thing that we need to do is to upscale it. This is being downscaled by 2. That is meaning decimation is being performed. So we upscale this by 2, opposite of that, right? And opposite of this is a low pass filter, so we'll use that low pass filter, right? So in order to get our original signal, we just need to take this particular signal, the sample signal, and we need to pass it through a interpolation or upscaling of these samples and passing it through a low pass filter, right? So that's how you get our original signal back, right? Now, moving on to part B of this particular question, decimating x of n by a factor of d is equal to 2 produces the signal, decimated signal x of d is equal to xd of n is equal to x of 2n, right? For all n. So now the only difference of this particular signal, right? This is the decimated signal. Remember, decimated signal, now the signal has been removed. All the zeros has been removed, right? If you compare this signal over here with the sample signal over here, all these zeros are gone now, right? In the decimated signal, we don't have any signal. This length of the when we are sampling over here in this particular case, right? When we are sampling in this particular term, what had happened is actually actually the signal size remains the same, right? If we had a, let's say n is equal to 10, the size of the signal was n is equal to 10, we would still have n is equal to 10. But now when we are doing the decimation, actual decimation, now the size has actually reduced, right? Now it has been removed. All the zeros part have been removed. That is the only difference in this, right? Now it says, show that xd omega, or basically the frequency response of the decimated signal is equal to the frequency response of the sample signal where omega is divided by 2, right? Plot the signal xd of n and its Fourier transform xd omega. Do we lose any information that we are decimated, that we decimate the sample signal as x s of n, right? So that is what we need to check, right? So let's avoid this, right? I mean, this is actually it says recall omega bar is equal to 2 omega. Actually, let me just explain you that. If you go back to page number 758, 758 of your textbook, right? If you go back to your textbook, if you are actually writing, the output frequency, right? Okay, here, this is the output frequency, right? So you can either see it from the point of view of the output signal, or you can either see it from the point of an input signal. Okay, the frequency of the input signal could be f of x. The frequency of the output signal could be in terms of fy. Okay, so what happens to the frequency response? If you go to this, right, the properties state if you are giving your output signal in terms of your input signal frequency, that is basically in terms of omega x, what happens is the values of the output frequency, right? Output frequency omega y is basically equal to d times omega x, right? So that is what this is. So in our case, our d is 2, right? And omega x is just represented by omega, while omega y is represented by omega bar, right? So let's avoid this at the moment, right? So we just need to show that our frequency response of the decimated signal is basically equal to the frequency response of our is equal to x of s, where omega is divided by 2, right? Okay, in this particular case. So what we do is the decimated signal, right, xd of n is equal to x of 2n, isn't it, in this particular case? So in order to find the frequency response of this using the the frequency response equation, right? So we can rewrite it as xd of omega, right? Omega bar is equal to summation of xd of n e to the power of minus j omega bar n, right? So let's just leave this omega, the bar sign at the moment, right? Now, based on this, you can see this xd of n is basically all even values of the sample signal, isn't it? So it is x or xs of n e to the power of minus j omega n divided by 2. N divided by 2 is basically indicating our signal is our signal is, how do you say, our signal is basically even, right? Okay, our signal is basically even value, right? Okay, so in this particular case, we will only be having a value when our n is even value, right? So we write this, we can rewrite this in terms of this, right? Now, based on this, we can replace, right? What can we replace? We can just take this n is equal to even. We can take this and we can rewrite it as this, right? Over here, x s of n is equal to 0 for all n, right? So basically the Fourier transform will give 0 value, so that it be omitted. So reducing down to this, if you see closely, if you just see the main sequence over here, right? So this now is in terms of n. We don't write it in terms of even number, right? So we just know that summation of x s of n e to the power of minus j omega n upon 2 for all n right? Since x of s of n is equal to 0 for odd numbers n, right? Which is equal to x, I mean, the frequency response of the sample, I mean, x s of omega bar upon 2, right? So it is just a step-by-step follow through, right? So this is what you get. So based on this, you can see that xt omega bar is equal to x s of omega bar upon 2. So if you relate it in terms of omegas, it is just basically xd of omega is equal to xs of omega upon 2, right? So based on this, you can see the frequency response, the sample frequency response is now being I mean, is now being expanded, right? The signal expands, or basically whatever graph we had, it is now expanding, right? Or the bandwidth is basically increasing of that particular graph, okay? Based on our graph transformation, right? The bandwidth is basically increasing. So if you draw this particular graph, right, in terms of xs of omega upon 2, to draw this particular graph, what you're going to get is something like this, right? The graph is something like this. And this is relatable to the original signal, right? But now the bandwidth has increased by 2. Remember, you have a signal, right? You have a signal. What happens to that particular signal? If you're I believe all of you are aware of graph translation, right? If you are if the, what do you say? Let me just write it out. If you have f of x, right? I mean, f of ax, right? And this particular graph is represented by, let's say this, and then if a is, let's say a is a larger value, right? I mean, this is for a is equal to 1. So what happens if a increases, this graph shrinks, isn't it? And when a decreases, what happens? Right, less than 1, it expands, right? So that is what is happening based on the graph property. If you draw this particular graph, if you draw the graph of this particular sequence over here, right? Whatever signal we have had for xs of, whatever frequency response we had for the sample signal early on from question number A, it is basically increasing, right? That is equivalent to our original signal over here, right? So based on that, our solution would be no information is lost since decimated sample rate still exceeds twice the bandwidth limit of the original signal, right? So question number 11.9, right? Consider the two different ways of cascading a decimator with an interpolator shown in these diagrams, right? These two diagrams are given over here. A, if D is equal to I mean, decimator is equal to interpolator value, show that the outputs of the two configurations are different. Hence, in general, the two systems are not identical. So if you have a signal that, let's say x of n is equal to x0, x1, x2, x3, x4, x5, so forth, right? And then you are decimating, your D and I values are equal to 2. So what that means is when you are decimating, you remove this second signal, right? Every second signal. Or when you are interpolating, so what happens is after every one signal, you interpolate so that signal, this particular part, let's say this, if you have one part, this particular sequence splits into 2, right? Okay. So if you have this particular signal, if we are decimating first, right, what happens is if you're decimating first, now we write the first signal x0, then we remove this second signal, right? Every second signal is removed when you're decimating, right? So in this particular case, we'll get x0, then x2, the third signal will be removed, then we'll get x4, right? And then x6 and so forth, right? Right? So that will be a decimated signal value. Now, if we take this right after decimation, if we are taking decimation first, after decimation, that signal that we have obtained passes through a interplotation, right? Interpolator, right? Yeah, right. Interpolator, right? Sorry for my pronunciation, right? Interpolator, right? Interpolator. So we have the decimated signal that we get after passing that through a decimated block, right? So we get this particular case. Now what we need to do is interpolate this particular signal. So what that means is to add a value to the first digit. After every signal we add a 0, right? Interpolate, right? Interpolate. So you add on to that, right? So we have this particular signal, we interpolate that, we get x0, then add a 0, x2, add a 0, x4, then add a 0, and so forth. We continue, right? So this is the signal that we'll be getting at the output side of this if we perform decimation first, right? And if our d and I values are 2, right? Upscale, downsampling and upsampling values are equal to 2, right? Now, if we perform the upsampling first, right, what happens is that we have a signal of the same signal, right? We have the same signal. What happens is after every first value, there will be a second value of 0 that we add, right? So we have x0, so we add 1, right? So this first term, just before x1, we have 2 terms in between, right? So x1, x0, and then a0, then x1, then a0, then x2, and a0, so forth, right? So what you can see is when you are interpolating, you are removing I minus 1 value, right? You are adding zeros of I minus 1 value. So you are adding, if our I value was 2, right? So we do 2 minus 1. So how many zeros do we get? 2 minus 1, it is 1. So we add 1 0 after each variable in that particular sequence, right? So in this particular case, we have 2. So we add 2 minus 1. 2 minus 1, we get 1. So we add 1 0, right? If our I value was 3, so what do we do? 3 minus 1. So we add how many zeros? 3 minus 1, that is 2. So we add 2 zeros after each term, right? Okay. The same goes for the decimator. If we have D, so how many terms do we have to remove, right? Or after how many terms do we remove the term? That is 2 minus 1. So we have 1. So after every one term, we remove a number, right? We remove one term, sorry, right? If it was 3, so after every like after the first digit, you remove 2 numbers, right? So that is downsampling by 3. Anyways, so when we are interpolating, so we are interpolating with a value of 2. So after every single digit, we add a 0, right? So we add zeros, and then it goes through a downsampler, right? Decimator. So it goes after the interpolation, it goes through the downsampler. So basically, we're reducing the sample size. So now whatever zeros we have removed is basically removed through the decimate, right? So we have the output as x0, x1, x2. So based on this, if you compare y2 of n and y1 of n, both of those two are not equal, right? B, show that the systems are identical if and only if D and I are relative prime, right? So a relative prime is basically two integers which are, two integers are relative prime if there is no integer greater than, if there is no integer greater than 1 that divides them both, right? So there is a common, the common divisor between the two terms are no greater than 1, right? So guys, just in case if this session ends, please rejoin after this, right? Anyways, I'll try to complete this, and then for the last 2 questions, you can just quickly join in. So let's say let D is equal to dk, and I is equal to ik, and d and I are relative prime, right? So, and the sequence that we have on our hand is x of n, right? X naught that has x naught, x1, x2, and so forth, right? And the sequence continues. So if we perform the decimation first, what happens is, remember, like I said, if I perform the decimation first, so what happens is this not x of d times k value will be the second value, and then so forth, right? So we have this particular value over here. So if we decimate this, we get x naught, and then the next sequence will be x of dk, and the next one will be x2 of dk, and so forth, right? So how do I explain this? Okay. Okay, in this particular case over here, on the top, on the first one, our dk value was equivalent to 2. Our d value was equivalent to 2. So that is why we got the values as x naught, x2, x4, and so forth, right? In this particular case, you can see if dk was 1, right? Dk was equal to 1. So the first time 0 multiplied by dk will be 0. Then x2, I mean x of 2. So the base subscript would be 2 multiplied by dk. That would have given us, remember, dk is equivalent to 1. So we'd have got 2. And next one would have been x4. So in this case, it would have been 4 times dk. So we can rewrite that in terms of this. So you can see that we get x naught, then x dk, where if dk was equivalent to 1, then this term would have been 1, right? Okay, anyways, so after, if it is decimate this particular sequence, we get x2 of n is equal to x naught, xd of k, x2 dk, right, and so forth. Next one will be x3 dk, x4 dk, so forth, right? So when you interpolate, so what happens is after every term, like I said, we add that I minus 1 number of zeros, isn't it? So after each term, you add I minus 1 number of zeros. So in this particular case, our I is ik. So ik minus 1 number of zeros is added after each first term, right? Same goes for the second term and so forth, right? So this is the sequence that we get. Now, if we were to do interpolation first, what happens is in this same sequence, x of n, what happens is after each and every term, we add ik minus 1 number of zeros, right? Isn't it? So x naught, and then you have a set of zeros, then we have x1, set of zeros, and so forth. And then if we had to, then this interpolation signal goes through the decimator, right? So decimation takes place. So in that particular case, what happens is that in that particular case, what happens is that this number of zeros, right? This number of zeros is reduced, right? So in that particular case, so we have a sequence of such, right? So in that particular case, if we see, in order for I1 and y1 of n and y2 of n to be equal, d is equal to dk and I is equal to ik. So k has to be equal to 1 in order for the sequence to be, pardon me, sorry, y1 is equal to y2 if d is equal to dk, right, where k is equal to 1. So that indicates d and I are relative prime, right? There's an example sequence, right? There's example sequence of given over here. Let's say two relative prime numbers are picked, let's say 2 and 3 in this particular case, right? And we have a sequence that has xn is equal to x1, x2, x3, x4, x5, x6, so forth, right? So if we were to decimate this particular signal, d is equal to 2. So what happens is after the first signal, we remove how many digits? 1, right? Isn't it? We remove this every second digit, we remove it, right? So in this particular case, we have x1. So we remove this d minus 1 d minus 1 elements from the sequence, right? So x1, we get x3, x5, and so forth, right? Now, if we had to interpolate this particular signal that we have after decimating, we interpolate it, right? So what happens is that we can end up with a sequence x1, 0, 0, right? Where our I is equal to 3. So like I said, when you are interpolating, so you just do I, whatever I value you have, I minus 1, whatever number you get, after each sequence, you add that number of zeros, right? Isn't it? So in this particular case, we have I is equal to 3. So I minus 1 will give me 2. So we add 2 zeros after every element. So x1, then after x1, we add 2 zeros. Then we get x3. After x3, we add 2 zeros and so forth, right? That is if we do if we compute decimation first. If we were to do interpolation first, what happens is it says we have this particular sequence. After each element we add zeros, isn't it? So we have x1 and then we have 2 zeros, x2, then add 2 zeros again, x3, add 2 zeros, and so forth. And then what we do is we decimate the signal again. After every second element, we remove after every after every one element, we remove this second element, right? So in this particular case, we have x1, so we remove the next element from the sequence. We remove this 0, so we end up with 1 0, and then we have 0 again, so we write 0, and then what happens to this x2 is removed, right? Remember decimating, we remove every d minus 1 element, right? After the element that we are on, we remove d minus 1 number of elements after that, right? So we are starting from x1, so we remove d minus 1 elements from that. So we are starting x1, so we write x1, then we remove d minus 1 number of elements. In this particular case, it will be 1 element. So we remove 1 element, so we write the next element, that is 0. Same forth, so we repeat that step, we end up with this particular sequence. So you can see that this sequence is equivalent to this particular sequence, right? So in this particular case, we have proved that if d and I are relative prime values, then I1 of n is equal to I2 of n, right? Okay. Guys, I want you guys to rejoin the same session again, right? I'll end this session over here, so you guys have to rejoin again.